Hi guys, welcome back to my math channel. Today we're doing differential equations again in the first order, and today we'll be talking about exact equations. So if you watched my first video on first order differential equations, I mentioned that there were three types of first order linear differential equations. There were linear, there were separable, and finally, there were exact, which is what we're talking about today. So I'm going to go ahead and define what an exact equation is. So here I have my short definition of an exact equation. Pretty simple. So an exact differential equation is a differential equation in the form of m of xy plus n xy times y prime. So the first order derivative of y equals 0. So this is homogeneous, and the opposite of homogeneous is non-homogeneous, so it would not be equal to 0. So a non-homogeneous equation would be equal to, say, a random function g of x of y and y. So in solving these equations, you want to make sure you are dealing with a homogeneous form so that the steps I will be showing you later will work and that everything in this definition is true. So this is really important, that your function is homogeneous and it equals 0. So what makes this exact is everything underneath it. So this is exact if and only if the partial of m in terms of y is equal to the partial of n in terms of x. So this is what makes it exact. And if this is true, the following is true as well. So this equation is exact if and only if my equals nx, such that there exists a function. Oh wait, this is incorrect. I wrote this incorrect. Sorry. Let me fix this really quick. Notation is important. So that there exists a function f of x and y, where the partial of f in terms of x is equal to m, and the partial in terms of y is equal to n. So if we look back to our original equation, this last part here means this. I wonder if I don't want to write, have all these lines everywhere, so I'm going to clean this up a little bit. So this right here and this right here are the partial derivatives of the solution f of x of y. So this is our solution to the diffy q, and m and n are the partial derivatives. Yes. So that is all the information. If this seems confusing to you, I think if you do problems, and I will do a problem right now, everything kind of clicks, and it really is beautiful how it all works together. So we'll do an example right here. So here's my example. It's asking if this equation right here is exact or not exact. So the only thing we need to check is if our m, which we can clearly see, actually, since we have this d of x right here, it's not exactly in the form we want it to. So we have to divide everything by d of x and get it in that form. So if we divide by d of x, then we can get the form we want, where you'll see in just a sec, where we have this dy dx right here, which is exactly what we want. So now we can consider this the form where this is m and this is n. Right? Yeah, so now we can consider this the form where we can kind of manipulate m and n. So let's check if this is exact. So remember, a differential equation is exact if my equals nx. And this is always important to remember. So let's compute that. So m partial equals, so if we take this, the derivative of this in terms of y, we can look at the first term, which is 3x squared, so there's no y term in that, so that's a 0. We look at the next term, which is a negative 2xy, and we do have a y term, so we just treat the 2x as if it's a constant, and we get 2x as the derivative of that, since the y gets dropped. And then the 2 is constant, so it's 0, so our partial of m in terms of y is negative 2x. So let's do nx now. So our first term is 6y squared, and this has no x term in it, so if we can, that would just be 0, and our next term is negative x squared. Since it is an x, we can just take the derivative of that in terms of x, and we get negative 2x, and 3 is 0. So we see that our my and nx are equal, so this function is exact. Yay!